Yep. So can you guys see my screen? Let me read the chat window. Yeah, that's fine. Good. So for the today's section, we will just browse you through. I think we are here and we'll talk about embedded system design and see if we can also touch base upon a little bit on real-time systems, and then the next 3 sessions purely on real-time OS. So all these 4 sessions are clubbed together, and here we have to start with. So, embedded system design is a very important aspect of building embedded application. And we are trying to go through an overview and then get into life cycle development, understand a little bit of test bed, understand build systems. I'll take an open source Linux view as an example, understand real-time systems for today, and then talk about, how real-time OSs characterizes themselves and how, they are different, knowing about the types of kernel, some CORDs. We'll also speak about 1 or 2 examples of CORDs. Also talk about strategies to build applications. You should also know about how your foreground and background system works. So spend some good time on your NPK kernel, and then we get into some very important aspects of application experience by using multitasking. You understand the concepts of tasks, know about them, and then get into communication, understand critical codes, synchronizations. Of course, there is sometimes we try to shuffle them, or we have placed interrupts over here, but off late what we have seen is covering interrupts prior to the task or background process makes more sense. So we might shuffle this flow to set ourselves. All right, let's start with small marketing analysis and then go ahead. So again, I'll not be trying to bore you, but you should know that, the connectivity in the system is demanding more and more electronics products all around us. Unlike where we used to have 1, or 2 electronics devices with us, now we have 6 or 7 or 8 devices. In fact, if you have a well adult, set of family for say 2 + 2, 4 people, easily you'll have 3 devices each, and then 2 devices each, and that contributes 8 to 10 devices minimum, and that's only consumer product. And there is a huge amount of market in this, and so prediction says that by 2020, 30 trillions will be the worth of embedded electronics production, and there is a huge, massive requirement for the developers, the designers, the testers. And you might see a quite improved computing and consumer and even communication. But slowly this is getting a little bit reduced. So communication is getting reduced, and automotive is getting increased, industrial getting increased. But it is all from International Data Corporation. So right, 2014 to 18 talks about some roughly 15% of CAGR, which is quite good enough. And the good insights from IC is that almost trillions of products are being sold, and then out of that 100 billion is being spent on developing those products. Now what's been very interesting is that if you were developing products 20-25 years back, as I said I think in the previous session, you used to spend a quite amount of money on hardwiring this stuff. So you used to spend huge amount of money on only hardware side. It means we contribute our algorithm towards the hardware side solution for almost 80%. Unlike today, we are giving equal weightage to some software systems as. So I explained this very clearly that there are scenarios under which you need to understand that ASICs are huge limited devices for massive production and cost, enhance, the tricky softwares and the effective softwares writing the needs of an R, right? All right. And what's more surprising is that overall money gets spent on integration and test, because the more and more you integrate and test your application, you make it more ruggedized, you make it more, predictable, integrated, and, it's integral a part of our humankind. So yeah, there is a huge amount of integration and tests going on. And unfortunate part always remains that, despite all what we spend, if you have projects coming up, roughly 18% of the project gets canceled within 5 months in the largest of the organization. And the ones which you get in hand, say, 50% late. And then, when you sell 20% of the products, you started with something, and by the time you release it is out of specification with 50%. So client says A, and you almost write B and say it's very similar to A, just a curve in the background down. Okay, so something like that, it's a joke. And the products that comes to market, that's roughly, having over budgets. Or maybe, if you're making late, then you may be ending up, you're out of the market, somebody else comes and pounds over those products, and then you're almost like gone. And we're finding, keep selling the product for 5 years if you can sustain in some way, and then you end up earning lower budget than you ever thought of. So quite a risk analysis, but what's important is the complexity, which is unfortunately making things harder. The pace of change, for example, if you wanted to think about a silicon architecture, now taking a decision on which silicon architecture is also a challenge. So should I go for MIPS? Should I go for Intel? Should I go for ARM? Should I go for something else? And then pick and so many, right? But if you're using ARM, has become a very popular, silicon architecture right now for major of the consumer section. I would not say computation and load-based enterprise class server kind of a capability, but typically on digital aspects of consumer. ARM has done a wonderful job for the last 1 decade, quite a good effect. And but still, like if you say V5, then say V6 comes up, there's 7 is coming, V10 comes, V11. So where do you change? Like it is too much fast. And then you also have something like connection effect. Every device is trying to connect. I'll have I2C, I'll have CAN, I'll have FlexRay, I'll have connected MIL1355BS, or I'll have some more buses, busting the system out. And what do I say? I should say that it's driving a lot of complexity. You have to write more softwares which can handle multiple such I/O interfaces, GPIO interfaces, more DAC to DAC, ADC to ADC. Need to be handled. Also, a lot of functionality is being demanded. Earlier, devices used to have 1 or 2 apps are working fine. People were happy. Now clients not happy anymore. They need hell of a complex and more functionality. And that's like tenfolds, last 5 years. And it's a very large part of R&D budgets. So we spend heavily on software now. And of course, you spend huge, but the customers do not want to spend too much money out. So they're very cautious. They want more and more R&D to be done with very less internal resources. So maybe, 5 people sitting can do a 50-man job, nothing like it. Or maybe 100-man job or 200-man job, So expectations are getting, really very, very complex and unlimited. And the thing is, only an upgrade can help you. And there are 5 key markets to look for. I see, industrial, aerospace, defense, and automotive really picking up. Digital consumers are slowly declining, and there are a lot of players, very easy to develop applications here in compared to other spaces like aerospace, defense, and automotive. They are very critical designed application, the last three. Even network infrastructure has become a part of social connectivity now. So, you need your enterprise class routers and the gateways to really keep working real time, and then allow all the bridges and application gateways to talk in a way that, and they are seamlessly connecting all the devices to us. But whatever the area you choose, seldom there will be a chance that you will be working on only one. You may need to work on several divisions. Gone are the days that you will only work on one layer. Now you have multiple layers to master. Let's look at them. For example, you may be working on core OS, and then your middleware, then development tools will be. You need to have knowledge of some management softwares. You should know some communication protocols. You should know security services based mechanism. You should know which core OS you're going to use. So maybe you should know about the reliability and compliances of your application. So these are some multiple areas nowadays. All in one kind of developers are required. We say it as full stack developer, like developer having 15 hands doing 15 jobs one shot. So there's a huge need. I mean, I'm not trying to sound negative. I'm just trying to say that there are certain serious changes, and it may be that you're a part of an organization where he tell you you're assigned only core OS job, and then you just sit on OS and do nothing. Or you may be only working on the reliability aspects of an application as a KPI indicators. When I say KPI, it's like key performance indicators. So, customers will have certain performance related parameters which they will be sharing for APC features. And you will be seeing that how all this can be achieved or tuned, So that's an aspects of how 5 key markets stacks, which you could work with. Or sometimes you might be working on some development tool. So you may be a part of build system. Somebody will be working on Make and Eclipse, or maybe Workbench, or some kind of an IDE connected with certain architecture and testbed. So that may be only your job. You keep working on, hey, I build a Android flavor of KitKat. Nowadays, it's a Freo version, backwards, some compatible. It's an ICE, or it may be the newly, jelly beans, or maybe Nugget, and so on. So Nougat. So I mean, I'm just trying to give an example of that. Build and version maintenance would be also part of your the job. Now, as we already spoke about, that embedded system is a subsystem which is a combination of software, hardware, and that's designed to do very additional hardware attached to it usually, and all the software is completely encapsulated by the hardware it controls. And we also took an example where we understood how embedded system is time constrained and often resource constrained, right? So time and space complexity drives this. One of the very conventional and a baby method is to derive the difference between desktop and embedded. Sometimes in the interview, they want to just tease you by asking these kind of questions, which has no sense on your, practical, pragmatic application development. So your job is completely different, but still, some of the developers really, or maybe, sometimes even managers, engineering managers, they will be setting up some calls, and they want to really know that, are you able to differentiate between these two specifics? So you should understand that desktop is a general purpose OS, and you do hell of a job there. Unlike, embedded systems have some single well-defined task, and it's targeted usually for a single user. So you'll not have multi-user. For example, even though you want to look for an alternate desktop systems like mobile devices or smartphones, they almost mimic like, they're a temporary system for you till you reach your, laptop or desktop. It's like keeping you engaged before you reach to that. Ultimate satisfaction is that when you get a big display, So meanwhile, it's an alternate system. So it's doing almost like a server job. It has a 4-core, quad-core, octa-core nowadays. Our cell phone itself is acting like a huge big beast or a server, I would say, So you cannot say that, mobile phone can be a single well-defined task. It's doing hell of a task. But just to contrast, it's a single user mode. You cannot develop application and compile the programs over there, right? So these are two essential differences which you should be knowing. And second, the processors are quietly different. Desktop, you have Intel, NVIDIA, and maybe AMD. But if you see the same thing with embedded, it's not true. They're a hell of a processor. I was evaluating, roughly we have 178 vendors today in Silicon world, which are offering different kind of chipsets. Now you can imagine the foothold of how big embedded and how complex and variety, of vendors exist, whether it's NXP or STCM or it's Altera or it's a Renesas, or it may be Intel's version, or maybe ARM's version from Samsung or LG, or maybe an Apple chips or anyone, huge. And Qualcomm, Broadcom. You keep naming and they keep evolving. So I said roughly there's a huge set of TI and Blackfin, Analog, Xilinx. Keep naming them, man. They're there. So they have done a kind of custom, I would say, applications targeted for them. So some of them are very good players in analog processors, right? So like TI, TMS, where the first ones to release the, I would say, the analog processor in 1987, I guess, yeah. And that's been great. Now you can see, so naturally the hardware is very custom built for a specific purpose. If you look at a school view, you'll find something like this. Every board, will have some kind of, so let's start with something on the right-hand side. So we have some custom devices. So either it will be a combination or a single ASIC or FPGA or PAL. And then that gets connected with some kind of a memory. So you may have non-volatile and volatile memory combination, and certain standard devices with I/O ports and peripheral controllers. You also have some kind of communication devices like usually RS-232, like UART and CUSI and Centonic and proprietary. Or, some kind of proprietary in a sense CAN. CAN is a Robert Bosch proprietary, something like that, control area networking protocol. So just like that, So there might be certain proprietary communication protocol which you would have developed that can be a part of your board, and that's how it makes it different, or USP. Also, you'll have some microprocessor devices which will be having something like 4, 8, or 16, 32-bit kind of thing. It may be a combination of DSP, RISC, or CISC. It may have a hell of debug test ports. You guys know how do you debug and test port? What kind of debugging ports are used for debugging in hardware? Have you debugged in hardware? So it's called as OCD, guys. OCD stands for on-chip debugger. On-chip debuggers examples are like BDM. Motorola started one term which we call it as background debugger mode, and then later on it became proprietary from as an open source accepted, proprietary to an open source, which is often referred as JTAG. JTAG stands for Joint Test Access Group, right? It's a IEEE 1149.1J specification, which you can download and understand the way at the time of CPUs being designed, how do you talk to them? So the use of debug port or a JTAG ports are to fuse the bootloader, or fuse the small OS or firmware on your hardware, So your hardware has a very special facility by which it can communicate to your PC by using a JTAG interface, So, and what's the purpose of that interface? So that from your PC, you could transfer your applications to the target board. So that's the purpose of debug port. Naturally, all these hardwares require software, and there can be application codes, there can be system codes like driver or BIOS. Some may be backed without OS, some may be having a real-time OS. Some may not have a head. When I say it is a headless box, it means devices which doesn't have any display. For example, your set-top boxes, or if you have any remote control, or if you have some, your routers or network infrastructure, they usually don't show. But if you have your mobile or television or something like smart key system, or smart internet-enabled panel-based refrigerator, they may have some display also attached with it, and allow you to do some other activity apart from their main job. So And remember, majorly the language which is ruling in these environment is C and C++. And of course, good to have assembly language and ADA in legacy code. A lot of codes are there for last 45 years, 50 years available in the system, which you have to sometimes make use of them. Right. Now, so naturally we're talking about the system, and now we'll try to learn a little bit more about a system from the perspective like processor, memory, and buses and supporting peripherals. So let's talk about processor. Like I gave an example of a special purpose processor like TMS320CXX DSP was one of the prominent early days processor. But most of the processors are a combination of CISC and RISC guys. Do you guys know what is the difference between CISC and RISC? Anybody? Who's going to try this? Difference between the RISC and a CISC environment. Nobody? I think somebody is trying to type or talk. You have a chat window. RISC is more complex since it's reduced. What is that? One, this is contradicting. So Sri and Kiran is fighting each other. Sri says RISC is complex, and Kiran says RISC is simple instruction. Guys, because one of the primary difference, what difference you're giving is a college, differences where you say marks differences. This is not the one. Come on. You can do better. All right. So I can tell you one of the primary difference between CISC and the RISC is the bottleneck of computing. In CISC, or sometimes we call it as a von Neumann architecture, was from Princeton University. And von Neumann was the one who actually won the Nobel for CISC architecture because of the manufacturing ability at that time the hardware had. So in CISC, the CPU tries to talk to program memory and data memory as a common bottleneck. So there is a common memory for both program and data. But when you say RISC from Harvard University, when it was developed, it has that for computation on a processor, there's a separate memory for program access and a separate memory for data access. So it means in a single clock cycle or less than 1.5 cycle, a RISC architecture can perform parallelism. In CISC, we use heavy pipelining mechanism in order to use parallelism. So these are two different approaches by which a CPU is designed. And it can be a microprocessor or a controller which can have everything on it. So can you think of why would you prefer microcontroller over microprocessor and vice versa, or a DSP and so on? Can you? Power consumption? It may not be, guys. May not be. So, okay, I've got one more answer on the chat window. Microcontrollers, built-in memory and faster memory. No. I think this fast word doesn't suit here because that's design. There are something important over here. Certain microcontrollers and versus microprocessors. A lot of people prefer microprocessors, but the reason for them is that they want more flexibility and they're willing to perform some manual interfacing for other components. So if you are at a more deep dive level and you have enough good engineering team on the hardware side, and you want more flexibility where you can pick and choose certain components, and then you can connect them based on your new design and the layout, then microprocessor could be a good choice. However, people who straight away wants to focus on application rather than doing these kind of unwanted interfacing, or I would say reduced interfacing. It's not like if you take out a microcontroller, you can straight away start making use of it. It also need at least a breadboard with some wire to connect them, and then there should be some mechanism to transfer data to them by using UV-prom or something, correct? But if you look at the level of interfacing which you're performing in a microcontroller versus processor is quite reduced. It cannot isolate. So you shouldn't be thinking like, microprocessor means interfacing is required and microcontroller means it is free from interfacing. Absolutely wrong. It reduces the number of interfacing and flexibility because it comes with this much of ROM, this much of RAM, this much of IO pin, everything inbuilt. So you cannot, extend them very easily. Again, if you have to do so, you have to incur some kind of an extension, and you're back to what you are doing in microprocessor. So you have to carefully choose between them. Now, often these kind of microcontroller and processor do not have an ability to perform analog processing. So we provide some basic functionality by using ADC-DAC, DAC-based connection, but they're not sufficient to perform complex signal algorithm. So one of the most important analog-based conversation can be the DSP process. So when I say digital signal processing, it means it has inbuilt ability to perform complex mathematical transformation for any signal which is being produced. So it takes signal and tries to process that from real world. So anybody can tell what is signal processing in short. If I were to ask you, what do you mean by signal processing? Digital signal processing. All right, nevertheless, see, signal processing, when I say signal processing, anything in this world which you see, hear and see and feel and look, all are analog in nature. Analog in the sense which has some variation. It is actually going to change from environment to environment. Hence, it is very difficult to track them or their consistency. It's very difficult to have them tracked for their correctness all the time, because it gets influenced by the another medium which it has it. For example, an RF, right? So we use different devices to increase their frequency or maintain their bandwidth, right? Similarly, we can think of if you have an audio and if you have to maintain those audios and you have to maintain the same record audios or videos when you're taking an image or an image framing or multiple image frame which can be converted to a video. So all these are a very complex processing capability, and signal processing is about reducing that noise in this environment. So digital signal processing is a way via which you take an analog signal and you try to apply some kind of sampling which is a representation equivalent to what an analog could be. An advantage of you being converting an analog real-time information from external world to an internal is either through sensors or something which you take. For example, you can take temperature sensors from external world and you can concretely convert them into discrete signals or digital signals. So advantage of that is you can easily manipulate, program, store, create analytics, and do hell of a job. So that's the whole purpose, that by removing those unnecessary noise, you can capture the real signal, and that is where the good DSP processors comes in picture, like Blackfin or Xilinx or even AD analog devices or even TI kind of a processors. So that's something which is very unique on DSP. So signal processing is all about reducing the noise or understanding those noise and removing of that noise and providing them a discrete way of representation in software so that you can play around with them later. All right. There's a diagrammatic difference between von Neumann architecture and Harvard. As you can see on the top, CPU has a common memory for address and data bus transaction. Unlike in Harvard, you have a CPU which has a separate memory for program and a separate memory for data transaction. Coming to memory also is a very important part in embedded development. You may have a combination of a lot of memory chipsets available as a part of your evaluation board or test boards provided by your vendor for your development. And they have three categories: volatile, hybrid, and non-volatile. Nowadays, hybrid flashes are more popular, like NOR, NAND, and XIP. NOR is a very expensive but very accurate and fast chip set based flash. NAND is for bulk data storage, so you can think of SSD and all an example of a NAND based flash, a bit cheaper in cost, but data stores a significant amount of data can be stored over here. So you can think of your thumb drive distribution or something where you have massive storage and part of NAND. XIP is a Texas proprietary, guys. I was working on it long back in I think 1999, right? So execute in place. So execute in place is a scenario for which we should take an example. Whenever you boot a machine or you start a machine, the entire program usually is stored in some ROM or a storage, permanent storage, or a flash or a hard drive. As you switch on, the boot code hard-coded program asks the program counter to start at some certain unique location on different devices. And what it does, it pulls that program which is there stored in hard drive and brings into the RAM area, so that it becomes faster. So if CPU has to talk to a flip-flop, it will be much faster rather than talking to a hard drive which is magnet. Or a CPU is much faster in talking to NAND, but much faster than flip-flop rather than using a NAND which is based on MOSFET. So MOSFET is slower and flip-flop is faster. So naturally your response time for an application running on a memory is going to be a very high profile one. And the applications, if it has to execute from flash, it is going to be hit by latencies, correct? So that's one of the reasons why XIP was planned, that there is something which is called as a boot time latency. So there are certain applications for which loading time itself is very high. Now, how I give you an example? For example, if you have to have a remote to be started, remote has a bunch of only well-defined features in few KBs. So if you switch on that with the battery, it cannot take 5 minutes to boot. I mean, it is impossible to think about such kind of devices in utility. Okay, so all these kind of different devices have some different boot timing. So instead of you starting the program, then transferring these all contents to the RAM area, and then loading the application for execution, may become a slowness or startup challenges. So there's a need for fast booting an interactive application. So TI came with a logic called as XIP flash. As I say, X means execute, I as in, and P as in place. Execute in place. So now you must have understood. Instead of we copying the content from a storage device to a RAM area, we'll use XIP flash to run the program from there only. It may not be as significant as RAM, but it improvises and improves quite speed in compared to a traditional access to a RAM or a ROM. Getting it, guys? So that's the idea on how your hybrid memories are being much used. Okay, see, in volatile memory like DRAM and SRAM is also very useful. Anybody who could differentiate between a DRAM and SRAM? What is the notion? If somebody says that, hey, you have a DRAM on your hard drive, on your target board, and somebody says SRAM on a target board, so what's the difference? How do you see that? Who's going to take this?
SRAM is much faster than DRAM.
Okay.
And the space required for DRAM is less compared to the SRAM.
I mean, it's more for high level, but there should be something more, Kiran.
SRAM is faster than DRAM.
That's fine, but that's okay. How is it faster?
Because DRAM requires charging and discharging of the capacitor, so it requires refreshment for every time you load and take out the data.
Every time.
Yeah.
So more than that, see, you're good. Okay, your answer is completely right. Okay, good one. But I would like to add some more point. See, that's academic what you're talking. Now you went up to a refreshment. How do you refresh the DRAM? Think if you're designing a board,
until the capacitor discharges.
Sorry.
You need to wait until the capacitor discharges and charges.
So how will you wait?
Memory controller do that?
No.
There should be some logic. Means whenever it reaches there should be some threshold voltage.
So how do you control that?
The threshold voltage?
It is charge. There's no threshold voltage. It's charge. Next. Okay, don't open me up. I'll go back to 25 years back. Electronics. As I said, I was a core hardware guy. My first job used to be loving K-maps. SOP and POS.
Okay.
But it's like 25 years back, guys. Yeah. So let me tell you, refreshment requires waiting or nodding, and the cycles waiting can be achieved by you having a delay generator being attached to it, and hence you require explicitly one dedicated timer which will do this job, and that's the answer. It means a DRAM must be connected not to a memory controller. Somebody said that. No. It will be connected to what? A clock, an extra timer, via which you will be having to refresh it, right? So timer can act like what? An event counter or a delay generator. So in this case, we need a delay generator. Whereas you have a controller being discharged, there has to be a recycle logic which I have to apply, and recycle logic will be feedback to from DRAM back to my clock cycle with certain amount of delay which we have to hard code it. So that's something which is DRAM. And if you have an SRAM, you don't need to do that. So what I'm trying to say is, as a developer, when you look at a target hardware, and if you see, hey, in this evaluation board, there are 10 timers, but there are DRAM, there are 2 DRAMs. So first thing psychology should understand, hey, I have only 8 timers which I can make use of them. 2 of them are already going to be hogged by the DRAM slots. You getting me? Yeah, that's the perception. So see, I do not want to just plain eyewash you the slides. I'm trying to probe you guys so that you not only revise yourself, but understand the perception of why we should know about them, so that, as an engineer, when you see a box, you should know the plus and minus of that box, that what becomes my limitation and what becomes my flexibility. If it was an SRAM, I'm free to use all the 10 timers for different aspects. Maybe if I don't have a watchdog timer, I can use one of the existing timer itself as a watchdog timer. I'm just trying to give you some, view on that. All right. So don't want to push you too much. Just be aware. What kind of, who asks these kind of, drill down questions or physical questions, There's a very popular company which does this. I can tell you from my example. Have you heard of a company called as Caterpillar? Caterpillar is a company which is very crazy about people knowing the hardware to its core level, typically at the physics level. And they, if you are into that team, typically engine side, ECU side team, they really want to grill you to this level. Even beyond this, they may get into law of equilibrium. They may get into SEUs, single event offset bugs, descriptions, and so on and so on. They may also tell you, okay, how will you create a clock? Who's going to answer this quickly?
Using oscillators.
And?
Phase lock loops.
Very good. Typically, an RLC is a good choice. Am I right? So if I take a resistor, inductor, L, and then I say a capacitor, if I combine all these three, it's almost like a weaker resonator, right? It'll start acting like an oscillation. Am I right? It may have dampness, not exactly like a crystal, but it will work, isn't it? So an RLC circuit would be a very good choice for you to say it can act like a ceramic resonator. Maybe it's weak, but it'll work. All right. Yes. Yeah, next thing which as a developer you guys need to look at your evaluation board is to look at the keyboard, sensors, transducers, and a lot of other things. So you must be aware, when I say keyboard, you should know 102 type, or it's just a keypad, or it is a 16 bar this pad, or this is QWERTY, or it's a capacitive, or it is a single touch, it's a sensor, or just a probe, or just basic knobs for your consumer devices. It's a pull knob or a touch knob or just a button or push button, or it's a PLC driven button. So, it's expected because you do not know which industry you're going to be thrown off. But there might be a lot of people who may be working on those lines. For example, if you're being interviewed by a company, say John Deere is a company which, they're a pioneer in agriculture, almost 180 years old company in US. Excuse me. And they make awesome trucks for farmers and agriculture. Having said that, there are certain models for which they use touchscreen and GPS mechanisms to integrate with Windows C classic old outdated applications, which is driven by C++. And there are certain applications which is built by the next generation Android and Linux-based boxes, which is running and driving OpenGL and then I guess Qt nowadays. They're putting the Qt on top of it. And there you have a capacitive touch-based application running as an LCD in a newer generation. Otherwise, you can see there's a pointer-based device where you have a lever via which you have to manually keep moving into seeing and enlarging the pages. So you cannot zoom in by using your tap your finger and do a Caesar on top. It doesn't work. It has to be a lever manually, just like a gas knob, and keep moving them, and maybe you can tilt them as much as you can to move from one place to another, to zoom and zoom in and zoom out. Kind of, so control knobs can be used in those ways, and the probability and precisions of them is actually programmed only for that. Just like stepper motor, you can be predictable once it's based out, right? Something like that. Also about output like VDL, LCD, LED, and then printers and so on and so on. So it's almost replicable to the previous one, but you have to be aware about the output devices. Also, there are a lot of other knowledges which these are like, they expect that software developers are very well groomed with their hardware knowledge in embedded. Otherwise, they don't make sense, It's as good as you taking a guy who's coming from a Java background and say, keep working on a project which will talk about reverse sensors in a car for a parking lot. I mean, it doesn't work, right? Because those guys will only talk about Java. He's a UI guy, app guy, and if you mix hardware, they get upset. So that's something which is expected, that these, like the timer, when it is used as a counter, when you do use a application health can be verified by watchdog timer. How do you apply a watchdog timer? How do you connect? What APIs do you use for a watchdog timer? For example, if you're using a VxWorks, you have WD start, WD end, and then attach and stop, delete, kind of an API. Or if you have a certain like QNX and SMX has, watchdog underscore create, and then you pass parameters, initialize them, and then attach an application alarm with it. It has a callback function which you can call, which can log something, or it can be connected to some kind of a PWM, pulse width modulator. It can beep and it can panic you, hey, come on, something going wrong in your system, and the time to look at your health. So watchdog timer usage, and the way you communicate, like ports, serial port like RS-232. So you should know at how your baud rates will be set, which UART is 16885, 16225, or it is how a TTL layer helps you to actually be compatible to your PC communications, or TTL transistor logic control to your voltage level transition should be known to you. You should know how to support baud rates and so on, guys. Again, a lot of example products. I'm just gonna skip them. Do you know this famous picture? Anyone?
Curiosity rover.
Yeah, of course, it is Sazonova, and in Mars it is having a still camera. Do you guys watch movies, by the way? So there was a recent movie, I think, from Tom Hanks, not Tom Hanks, I think this guy, my favorite, The Martian. Have you seen that?
Yes.
Matt Damon. Have you guys had a chance to see a film called as The Martian? No?
Yes.
Oh, yeah. Awesome. So, The Martian is a fantastic example where you are going for a, unmanned mission, and then a person is, not able to come back, and is trying to show you the same thing, that this had lost the contact, and this guy who has reached the Martian is trying to tilt this camera. There's the same camera at the ground level also, and they try to fix it and make it correct, okay? That's the same thing. It is driven by VxWorks guys, and runs Intel A085. This is Chandrayaan, one of the most popular super hit projects from ISRO here. It has been powered by PowerPC and MIPS architecture with x86, all the three. You can see your Boeing 737 completely powered on with Tilcon graphics running with VxWorks powered by PowerPC architecture. This is your cockpit. It has hell of a physics system over here. It has OpenGL display on the right-hand side. On the left-hand side, the screens are showing is completely on Tilcon graphics. As I said, the platform is VxWorks and the hardware architecture is PowerPC. You can also see some of the very popular components in a car. Modern car has a lot of things here. So you can see CAN, GPS, GSM, LIN, local internet connect, internet most, which is the framework. It's a media-oriented system transport by which you can talk from one media tile to another. You can see pretty well, segregated components placed over here. Your instrumentation cluster IC, where you can see your typically speed and then distance to end, and if there is an alarm for fuel, and if your door is open or closed, some animation. They use CANSI, they use Qt, they use WS widget, UIs on top to bring these kind of application. Some of the very big players like Visteon, Harman, then you have Philips. I would not say Philips, I'm sorry. Even Panasonic, you have, they're like giant, they're huge, they work hugely on numbers. In Delphi, Robert Bosch, biggies, these are like Continental. The top companies are working and investing on all this. I mean, I shouldn't be talking car names like Tesla, BMW, Daimler, Chrysler. They become mostly your client. But the one who works on the breakdown components aspects are like manufacturing side, like Visteon is fantastic in Sofia in France. They have huge manufacturing power plant. So So, I mean, that's their bread and butter. Medios and so many, right? You can also see, one of the most complex, and you must have seen in, on Google also these kind of pictures nowadays being shown, that this is an example of how all the devices from different verticals are going to get connected. And when I gave you an estimate of 30 trillion, these guys are blowing up to 50 trillion over here. Says consumer and home devices are connected, healthcare devices, personal wear devices are connected, retail gets connected, industrial gets connected. So connected has become the new mantra in the system. Everything gets connected. And you have a big boom of network, internet, which is the most reliable thing in the world, they say now. And if your machine is not connected, you feel like this is not the machine which we can really make use of. Imagine, if I give you a PC and I say, hey, this is an awesome Mac, PC, but it doesn't have an internet. What's your answer going to be? To the hell with Mac. I don't need such Mac which doesn't give me a browser, right? So today, the people who want log into any OS, Tom, Dick, Harry, it doesn't matter. Whether you log into Windows, whether you log into iOS, you log into Android, you log into Linux, or you have a Mac, or you may have a Rocket operating system, doesn't matter to you. Once you log in, the first thing you want is internet. Net doesn't work, it's a piece of no use to me, right? So you can imagine, John Chamber, who was an ex-CEO and now chairman at Cisco, said that, internet is the next equivalent thing to education. So after education, this is the next equalizer in the life. So as important education is in your life, the next has become internet. And that's so true, right? So that's the connectivity factor. You can see embedded devices are going to arrive. So you have to understand, connectivity is a backbone now, a media now, via which devices will talk from one vertical to another. But to build these verticals, embedded guys will always be required. If you do not have the basic sensors, you do not have the level one architecture hardwares, you don't have L2 layer computation, fogwares and all, you will not be able to communicate and connect. Why do you need a network when you don't have a devices? And evolution of devices is always going to demand fantastic embedded developers. Of course, complexity will be more protocols will be needed for you to learn, but there is a lot of work done already, guys. Okay, so you need to pick up from there on, right? Let's look at some of the development environment. So if you are coming for development environment, you might see a lot of things, so as a knowledge. So, an IDE controls most of the things, so you don't need to do everything manually, but surprising, IDE hides a lot of things which is going in the background, so it makes you difficult to debug your application. That's why most of the people love if you can say, hey, I'm a command line builder. Say, wow, man, you're not cool. I mean, this is an accent which you'll be hearing most of the time from embedded developers. So it's a notion. IDE is a very good tool. IDE must be used for certain, there are certain vendor specific IDEs, like Renesas may have its own, Workbench from Wind River, now Intel may have their own IDEs. QNX with Renesas, Momentix may have a different IDE. So integrated development environment is a software tool which comprises of a very nice editor. It supports multiple language. It allows you to have nice debugging capabilities. You can debug software and hardware components on that. It's an awesome build mechanism. It has a lot of configuration for different compilers like Xcode or code blocks or Eclipse CDT or a plugin on QNX Momentix or Workbench. So a lot, numerous of IDEs which is available. And they provide healthy compiler, assemble, linker, loader, and locator. They have some build systems like make or automake kind of things by which you can automate your build, okay? On the right-hand side, you also have connected some hardware tools with them. So most of these embedded IDEs, They provide ability to connect to hardware tools via which you can program the devices. So some device programmer, usually some debugging ports like BDM, JTAG, Nexus, or some older versions may contain ICE in circuit emulators, ROM emulators. Sometimes you might be going down to using CRO and passive checking for your components using a multimeter and logic analyzer. I mean, so all these skills are required, guys, you know. So this is where you are differentiator. Taking a Java guy will not work. I mean, you really need a hardware guy who's aware about these all uses, you know, so that you can always, you know, if required, you can drill down to this, you know, but they cannot. They don't even know how to use a multimeter, you know. I mean, a lot of engineers do not know that way. Now, when you develop, you know, IDE is usually installed on, so let's look at this, you know. So you are sitting on a desk on a right-hand side. On the left-hand side, you can think there's a small evaluation board given to you, which is a test bed. You have a communication by which you will be transferring and talking to the device. So IDE gets installed on your PC. You may be using a Windows platform or a Mac or a Linux host machine. So we call it as a host on the right-hand side. And this development is called as cross development, right? So embedded development is usually a cross development. Cross development means write on desktop similar machines, but run on some other architecture and machine. So usually IDEs and all run on certain architecture. And then when you build your application, what you need to do is you download those components of software on your hardware. So hardware may be your PowerPC, MIPS, or Alpha, or ARM architecture. And then it might have some application RTOS on some debug agent built together in a single image or segregated in images with different partition on MTD. And that can be deployed by either JTAG or, you know, using some Ethernet-based cable via which you will have mechanisms to download and store them in the flash forever. And once you remove this connection and start this box, it's more like, you know, if everything goes right and your applications are designed as per the requirements, as per as the expectations, then you have a nice box little running. This is a diagrammatic view of different kind of editor. On the left-hand side, you can see we are using, I guess, a workbench. On the right-hand side, left-hand side, you have QNX Momentix ID for automotive. You can also see on the corner left side, you know, on a left side, this is an Android box. So you can see Android emulators are running here. Again, on the right-hand side, you can see there's a VI. Okay, so it's a VI. So if you look at, you know, it's a command line tool-based development. So we'll see how to use them all in Linux. Now there are certain application strategies, guys. Now this is also worth knowing. So application strategies like when you're building for desktop and then desktop. So the very popular build process, remember these things will be repeated with hands-on in a couple of sessions from now. So how do I correlate you guys? Let me show you in Excel. So, you know, when we reach to the place on the 13th hour of this session, then is where we'll repeat this stuff, whatever we're talking about, okay, the build session. So today we are just on design and real-time systems. So, you know, you can see here, this is a desktop build. It means you can think of that machine is, you start from the bottom up, approach. You can see bottom operating system image, which is over here. Okay. So this stuff. And then from here you go to boot. So it starts up and it's loaded in the memory RAM and it's running. And now it gives you an interface where you have an IDE. So this is your entire IDE based process, which we spoke. IDE will have some compiler, assembler, some libraries, and they will generate the source code to an object code. Object code gets connected to the linker, and then linker creates an executable code, and this exe gets loaded by using a locator. So you map this application virtually or even physically by linker scripts to a specific area in the RAM. and then you have your applications running as long as your machine is up and doing while one the same job again and again. So that's a strategy for desktop development. However, on an embedded application, seldom it will be that everything is pre-running. So here what we do is everything sits on, the target actually is planned to sit on top. So I can tell you that, for example, here. So this entire application is going to be your target. This is my app, and it has to sit over here. We have to flash this by using utility. And ROM burner will help me to place them. So my application comes and sits over here. This is my app. Okay, this is my app. And whenever power will be on, traditionally, that application will be copied to the RAM area and will execute. But to do these all things, what we do, so you can see there is no notion of that people already have the box running up with OS and then you have to download. No, it's a hardware for which you have to flash everything. So an application strategy changes when you build the IDE from that vendor which they provide. Okay, they will ship you some kind of a kernel which you are going to make use of it. Usually some commercial off the shelf, maybe VxWorks, QNX, or some other, custom form of Linux from Broadcom or from Intel or customized for something. Then they may provide some library support, which is unique to your applications. And then some tools like assembler and compiler. These are cross compiler and cross tools chains. So I would say X compiler and assembler. And we don't say cross assembler. Assembler means it generates architecture specific. So it's the same. All these, intermediate files actually which are getting created over here gets clubbed together, and we write a linker script. Linker script is also called as scattered files. Usually it's a small piece of information which allows you to say what part of the program will place where. So linker connects that program, creates an exe. While exe is getting loaded, that linkage specification, which it takes it over here, that is what a locator will help you place the program. So, it will have the map of the entire program, like starting from the origin 000, where should it go and sit at FFFFF or FFFFFF or B followed by 7H, depending on, the memory map of that architecture. Usually all the vendors will ship one set of PDF, which will have schematics, which will have interfaces, chip select logics. It will also provide you essential, interface addresses, base addresses, which it starts with, so that when you write software, so you know where to write, which port to write, and so on and so on. So that's on the, build system. Now, when you write application, there are two strategies. One, you write an application directly, okay, and you build directly this application to run on the hardware. This is old age programming, like, writing a program for a microcontroller, create a hex file and dump it. The problem with this kind of program is that small change means the entire application has to be rebuilt and rebuilt. So it's not very portable. Okay, you have to keep doing rebuilding of a small change. For example, if I say you that on a particular port, instead of having a 30 millisecond or microsecond of delay, you have to generate a 60 microsecond of delay. Once again, you have to go and make changes in the code, and so you have to rebuild its entire application. You have to again find the right number to which will go and sit in timer, and so on, and then rebuild that application, convert hex, and then dump that by using bird notes. Okay. But on the left-hand side, when you have a real-time OS kind of strategy running in, operating system abstract, though it is a little bit delay on the hardware, but you can think of improvising the hardware and putting some software as an overhead is fine. So on this agreement, OS becomes more portable way of your application development. So what application does, it uses some standard libraries. On the left-hand side, you can see here certain colors are being shown. Different kind of libraries are being used by application. They create an exe, and OS provides interface by which it can, allow your application to talk to hardware. An application by no means, okay, an application by no means can talk to the hardware directly in this kind of environment. It's not allowed. it can always talk the the program via OS on system calls. This is perfectly fine. This is okay. It will always go to system call. System call internally will do the job on behalf of you. So OS will act like a commander on behalf of you, a kernel on behalf of you, and he will be able to write privileged codes for hardware. You will just make a request. By doing this, what happens is, if something you have to make some changes, you can straight away make that API and start recompiling this program. So tomorrow, this program becomes more portable. So if you have some standard OS determined on targets, you can keep changing application with few or no changes and becomes more portable, guys. Okay. A small diagrammatic view of how your desk may look like. If you join an embedded company, you may have some target boards, you may have some other laptops, one to test on Mac, one to test on Windows, one to test on Linux. Some may be connected, some target board may be connected, and you may have to record some information, so and so on. Some camera is connected, you want to record those details. You may have some software running to control them, and so on. Evaluation board example. This is an example of friendly ARM board from Samsung 926 eAge ARM architecture. It's an ARM 9 architecture. So it is V5, version 5. You can see so many interfaces over here. It has an SD card too. You can boot an OS from SD card. You can boot the OS from flash and whatnot. So, your core processor over here is this. This is your core processor. And these are your DRAMs. These are some UARTs. You can see the serial ports. So this power on and off. You have a NAND and a NOR switch on the other side here. I'm just trying to show you this. Then you have user button, push button to do some kind of programming, home, next, next kind of thing. USB host side. A variation you can take and you can move this manually. ADC test for an analog variation, you can give this. All the GPIO lines given to you. Display connected with it here. Then you have something like JTAG interfaces. Let's see where is JTAG. This is 10-pin JTAG. Because 6 is sufficient, but here you're using 10-pin. Mic in, some microphone in. You also have a pulse width modulator. You can have a speaker here, you can think, and so on. And this is your network chipset, and so on. Now going forward, to understand application development, we have several builds, and as I already explained you that the cross build is the most important environment in embedded. So what we do, we use a host. Host is a PC. And we use some build system via which we create the target specific application. That's the idea. How do we do that? To understand that compilation machine will be a PC machine, which will be triggered by Intel x86 architecture. But the output which you will generate will not run on x86 architecture. It will be targeted for ARM architecture. So you need to somehow find a way to push your application from your PC to the target architecture. And that's what is called as cross builds and testing. To do them, we will be using these, tools. And right now, I will not be talking about this. Once we reach the build system, we will have more connectivity about this component. Okay, guys. So as of now, application development, I will be pausing up, and I'll be skipping up this in order. Rather, I would like to conclude with certain very quick features in embedded, So as a summary, okay, once you have an access to a Google Drive of mine, you will have all these, PPT materials available for your, testing purpose. So the very important aspects of the basic design goal is reliability. So your program is going to be mission critical. You should know whether it is life threatening or not. You should know your application will keep running 24/7, 365, just like CNN, IBM. It may not reboot, but can have resets. Same thing from performance perspective. You should be able to write multitask and schedulers. You should be able to write optimize IO. Same running one and cannot boot. Why are they different? To conclude today's session, embedded systems are different because they are dedicated to specific tasks and PCs are generic computing platforms. Okay, there are a lot of processors architecture supported in embedded, unlike desktops are having a bunch of 2-3 processors. Naturally, so the ES or embedded systems are usually very cost sensitive, right? You can think of the use of a goldsmith hammer cannot be gained by the sledgehammer. So I can't keep using Intel Core 2 Duo i3, i5 in every application, correct? Again, naturally, it has a lot of real-time constraints. It is not necessary that every embedded application will be using an OS, but if it plans to use an OS, it will be some kind of real-time OS. Maybe proprietary, maybe homegrown, maybe commercial, but it will be a real-time OS. Also, there are more side effects seen in terms of the failure in embedded applications or systems, right? So it's more severe, unlike desktops. I mean, there's no matter of life and death. It also must, operate under extreme environmental conditions. So that's another very important aspects of embedded application, that whether it's a industry, uh, certified product, say for example, IP stands for what? Ingress protection. So IP68, it means you must have seen, nowadays even phones are telling I am IP65, IP66, IP67. It means what? This is a code. Ingress protection is a mark saying that it is weatherproof, tamper-proof, waterproof, and all those things. Sunlight proof. So if you leave them in the sunlight also, it will be able to bear it. If you drop into your water also, it is proof, and so on. Weatherproof. So that's an example of operating under extreme environmental conditions. So they're built for certain standards. It's very rare that embedded application will always have a hard drive. For example, Steve Jobs was the first one to start embedded devices in 2001-2 by having an iPod first generation launched, and they were having hard drive, which was much cheaper in terms of storing the number of songs he wanted to. But usually embedded applications are stored in ROM or flashes. Yeah, there's one of the biggest challenges. How do you transfer and talk from embedded processor to a desktop machine? Because desktop is the source where we will perform the development and download the application, correct? So one of the easiest way to understand this will be that it has a OCD like JTAG or debugging circuitry, what we call it as. And last but not the least, that embedded system actually has limited resources, and hence they need perfect tools. And usually these IDs and all are shipped by the vendor itself. So if you buy a Samsung board, Samsung himself will provide you a CD or some kind of downloadable links via which you can download the required tools for developing your application. Okay. So guys, for today, I'm going to just keep it over here. And when we talk tomorrow, we will extend the information on what is a real-time system and how it works and so on. And then we'll move on to understand about the real-time kernel. We understand the operating system behavior. A lot of very important terms, which is a part of interest for most of the employers. That are you clear with these terms? So I want to ensure that our foundation level goes pretty good. Okay. So for today, let's keep it here and let's catch up tomorrow again, guys. And thanks for you having me here. Have a good day. Bye. Take care.